A hush descended upon the audience. Excellent. Well, oh yes. I guess you don't need the music. So welcome back into the meteorological fall, I guess, right after September 1 or after Labor Day. Traditionally, has been the deal. I'm sending stuff out, as you know, on Fridays as a summary of what to do for the following week. So this week, there's a homework due, homework 2, which we finished on Friday. There's a quiz for the stuff on Monday, which of course was a holiday, but just to keep in sequence, hopefully, I was going to insult your intelligence by sending you an email yesterday to say maybe you should look at 3.1 before we do 3.2 on Wednesday, but I didn't insult your intelligence. You can get by today without that, but there is an extra credit quiz available, which will close Friday at midnight, and that will be the sequence of things that we'll do. So any quiz that's kind of extra credit that's, I guess, not required, but required for your own education, the due date for the quiz will be 2 periods hence. So it gives you some kind of window to be able to do it. So we'll briefly recap the information from talking about fluid statics and pressures on structures, which was covered in 3.1, and then move on to kind of extend it. So that's the plan for today. Obviously, the relevance for this is not so much fluid pressures on structures, but the whole idea of getting a boat up is by pulling on the centerboard. And by pulling on the centerboard, you're exerting a moment on the boat. And a moment is one of the key features that we deal with to be able to look at defining fluid pressures on structures. And so that's the basis from which we'll work from this. I'm going to stop that now. And so I guess I don't want that, but I do want this. So let me find the right place. We're covering a lot of ground. And so this is where we are. I'll recap exactly where we are. And to do that, I'm going to use this. And this, just because I can. All right. So we are here and here. And we are, so I'm not using a blunt instrument. So we are 3.2. On structures. And if you looked at 3.1, you'd have seen things like comets, the first British commercial airplane, jet airplane after the war, falling out of the sky because of the pressures inside would rupture the cabin because of stress fatigue. But we'll make the point that there are 3 things we need to know in looking at fluid pressures on structures. So we know, for instance, if we're looking, typically we're looking at fluids. And so we know that when we look at fluids, that from the free surface, the fluid pressure goes down as equal to, if this is Z, this is equal to minus gamma Z, because this is negative, or equal to gamma H, I think we've called that. So H is a positive number. And so we know that with this pressure distribution, if we have a plate on which this acts, which might exist here, then we know that the pressure distribution that would act there would be given by this triangular distribution. And the magnitude of that pressure would be given just by summing up all the components of it. And so what we end up doing is we end up taking a coordinate system, and from that coordinate system we will use just this once, instead of this vertical direction z, we'll call it y, and we'll call it x. And so if we take a plate that is present within this, don't care, then what we can do is we can take a small little differential length, which we'll call d sub y, some width to this, and if I kind of draw over here a perspective of exactly what the pressure would do as you go down, then it would have this distribution of pressure down to the base of this plate. And this would be the same as what we have here. And so what we can do if we want is we could calculate the force that would be acting on this plate, and it's going to be equal to the integral of pressure times dy times w. We know that the pressure is equal to unit weight times y, at any point. And so what we could do is we could integrate this, and we'd come up with a width, an integral of unit weight y dy, and if we do those integrals between 0 and y bottom, I suppose, we'd end up with w gamma a half y squared, all evaluated between 0 and y bottom. And if we looked at that for this particular case, it would be equal, and split it out, we get a width times yb, just taking this. So if you substitute this into here, this is 0. The only one is going to be yb, so it's going to be yb squared. So if we take the width, we take yb, we take the unit weight, we take a half yb. Let me write it the other way around, if you haven't written it already. And hopefully that should be this whole thing. And if we divide that up into what these things represent, so this here is yb, bottom. This is y0 at the top. So the total force acting on this plate, which will be the same acting on either side, is equal to an area, the unit weight, and the depth of the centroid. Always. You go through a much longer derivation to do this, but it always works out the same. But this is the way that we've stated. And actually in the book, just to be consistent with the book, this would be the area, the unit weight, and the depth of the centroid h sub c. So let's keep that as one component. The depth of the centroid is equal to this term here. So in this particular case where the plate cuts through the surface, if you imagine drawing a line from edge to edge, then the centroid of this plate is a half y base, which is equal to yc. And so this is a standard expression. So this is the first of the things we'd like to get. We'd like to get the magnitude of the force. How big is the force that's acting on this plate? And this is always true. This is always true so long as the depth of the centroid is measured from the surface free surface. So, in other words, if you imagine this plate, instead of being at this length, this location here, imagine we move this plate down to this point here. And if we extend this, then the pressure distribution will look a little different. But the expression for the magnitude, so what this will do is it says that there's a force of some magnitude, which is F, which is the integration of this distribution, and it's equal to this. If we look at this behavior now, the force that's acting here would be some magnitude of force here, which would be given by the same amount. The area would still be the area of this plate. The unit weight would still be the unit weight of the fluid which it finds itself in. But now the depth of the centroid is going to be the centroid of this plate. So if you look in perspective as to what this plate would look like, again it's going to look like this. This is the centroid, and so this is the centroid here, which is at mid-height. The centroid of the plate, not of the distribution, but the centroid of the plate. And so it's at this mid-height here. And so if you look at the pressure distribution you get here, very straightforwardly, what it's saying is that if you calculate the pressure that acts at this centroid, if you multiply it by the area of the plate, which is the height multiplied by its width, then what it's doing is it's taking this portion of the distribution off here, and it's adding this portion here. So it's adding this amount here, and it's subtracting this amount here, and that's why it physically is correct all the time. So this expression is the first of our expressions which we need, which always gives us the magnitude of the force acting on a plate. Always true. Always true so long as this is the area of the plate, this is the depth of the centroid of the plate below the surface, and this is the unit weight of the fluid it's in. If it's in air, then this is so small that the change over the length of it. If it was in air, the gradient of this would be so small that this would be basically vertical, and so it would still follow that the pressure at the centroid, if you multiply it by the area of the plate, would be equal to the sum. So in other words, if this portion here, I guess if you want to divide it up, this term here is equal to the pressure at the centroid. In other words, this magnitude here, this length. So it's good to get a feel for exactly what that is. So that's the first of the recaps of the things that would have been in the slide the other day. The second is a trivial one, I suppose. But it is if you have two forces, which is Fx and Fy, then the resultant of those F sub r is equal to, you could tell me this just from Pythagoras, Fx squared plus Fy squared square root. So that might be something that we might want to use if we're trying to figure out if we have two forces and we're trying to distinguish between them. And so the other two things that we might like to figure out are, one is the third one, I guess. Maybe I'll write it down here. So, okay, everyone with that? So that gives us magnitude of the force unequivocally from this. The magnitude of the resultant unequivocally from this. The third case is that the force acts at the center of pressure. And so, and also, maybe we should also write this. The center of pressure, C of P, is not generally equal to the centroid. Very important. And so, if we take a distribution that looks like this, as we've just drawn, so this is the free surface up here. These are the forces that are acting due to the pressure as you go down in depth on this plate. We've called this Y. I suppose this would be, in this magnitude, this would be pressure. We've said that the magnitude of the force, horizontal in this case, is equal to unit weight, depth of the centroid, times the area of the plate. If this happens to be a plate which we draw in perspective like this, then definitely the centroid of this plate is at mid-height. And so if this is H, then this is HC, which is equal to H over 2. But the resultant force of which this is acts at a depth of, for this triangular distribution, of 2/3 H and 1/3 H from the bottom. And the reason for that is that if you look at the resultant, if you look at the sum of moments that we have acting on the system, the moments equal some lever arm multiplied by a pressure multiplied by some length and area. So this would be an incremental force, dF, and this would be a lever arm, which is Y, if you like, coming down from this. And so what it has to be is that if we could choose a location here, then this would be the location where all the forces acting above this, why don't I change colors just because I can, all the forces acting above this multiplied by their lever arms. And so the individual lever arms are just the length away from this point. And all the forces below this acting horizontally, purple maybe, can't really distinguish that from the red maybe, acting in the other direction. So these are acting in this direction, these are acting in this direction. These would be the behaviors that balance this. And it turns out that the centroid of this distribution, this pressure distribution, is exactly where that force acts. And so that's the other big message out of this. I'm going to try something that I wanted to, that's still there. This is I'm going to try something here. Here we go. See if this works. Oh, that's fantastic! Isn't that frightening? So you can see it. Good. See all the pictures at the bottom? It's not narcissism at the bottom. It's passport photos. So here's the deal. I'm not sure how this is going to work. So this is what we've been talking about. This is our plate that we have that sits in the water. It has a fluid pressure acting on one side. It'll be completely reacted by the same fluid pressure on the other side, so it's in equilibrium. This is the coordinate scale that we've got. I guess it's backwards. Is it backwards for you? I guess it probably is. So, from what you see here versus what you see here. And so this is all we've done. We've taken a little differential. We can have a fluid pressure that acts here, and if we calculate that fluid pressure multiplied by the area it acts on, that gives us a force. If we integrate it down here and across, then that gives us the magnitudes we get. If we want to be able to figure out exactly for this how to calculate where that average force is, it's in the centroid of this. The centroid of this, by definition, I can't really draw it here, but I'll do it for you here, is kind of this, right in the middle. And so the meaning of that is, the definition of a centroid is that if I put my finger at that balance point, right here, and just leave it there, then this will physically balance on my finger. That's what the definition of a centroid is. It means the weights from this single piece of paper pulling down progressively further away from this point, multiplied by the lever arm which they pull through, exactly balance each other. And so this is the balance point where those are equal. If we look at the fluid pressure distribution which is acting on this, so this is where the origami comes in. So let's see if we do it. So I'll do it from the top. See if I can pull this off. It's not quite going to work because of this, but we can get the picture, I think. Forget the fact that in my origami here, that now the paper is more than one paper thick. This is the pressure distribution. And so this, if we look at it here, is exactly what our system looks like. This would be a system where the top of this plate intersects the surface, right? Because the fluid pressure is 0 at the top and increases linearly downwards. If I pulled it down below the surface, then this magnitude here would be finite, and this would be added on by the same amount. It would just be increased by that amount. But the reason for me showing you this is that the location where this fluid pressure acts is not at the centroid, where my finger is showing you now, but it is at the centroid of the pressure distribution. And so if you imagine this pressure distribution being this, the balance point for this, if this was just a single sheet of paper, would be 2/3 away from this end and 1/3 away from this end. That's where the moments that are acting due to the stuff on the one side of my finger, on the thick side of my finger, are exactly balanced by the components on the other ones. And so there's a certain symmetry in the fact of the understanding of these centroids. And so that's something that's perhaps worthwhile knowing. That's the basis of what we're dealing with. That's cool, don't think? No reaction. So the other thing that comes out of this is that if we look at, go back to our stuff and carry on from where we were, this is kind of the summary of where we are from last time. So it's worth reiterating these points because they're important points. This is exactly what we've done so far today. We've said that always the magnitude of the force acts normal to the surface. It's equal to the pressure that acts at the centroid multiplied by its area, for what we've talked about. We can always resolve forces by just looking at the vector sum of forces, just Pythagoras. And importantly, this resultant does not act at the centroid of the plate. Does not act at the centroid of the plate. It always acts below it for a linear pressure distribution. Always has to act below it for a linear pressure distribution because this is getting thicker, progressively thicker at the base. And for a linear pressure distribution that intersects the surface, it'll always be 2/3 down. If it's a pressure distribution that's below the surface. So instead of hitting the surface, if it's lower, then it would be out by a certain amount, where this amount here was the fluid pressure. Then we have to figure out exactly where that center of pressure would be. And that's our next goal in this. So this is the deal here. It turns out that we can actually figure out the location where it acts below the surface. It's equal to the depth, the y-coordinate of the centroid, but plus a small amount. So the y-coordinate of the centroid is always going to be the location of this plate below the surface, the y. And it's actually, the other thing is, the y, we've made a distinction here between h, which is the depth from the surface vertically to that point, which turns up here, and the definition of y, which sometimes is that same depth, but if this is tilted, the inclined distance is going to be longer. So this really is y and not h, and so you should remember that. And this is called the second moment of inertia, second moment of an area around the centroid, which we'll talk about, and these are as well. So that's our next task, is how to figure that out. So we could go through this big long derivation here to get to the same point of this, YR, you see boxed in red there, but let's not. Let's do it in two lines instead. So this is the idea. This is what we've just done here. We said that the force is equal to a pressure times an area. We can write the pressure in a certain way, and we get the magnitude, which is Fr is equal to gamma A H sub C. If instead of taking the forces, just by integrating them, we take the moments. And the reason for taking the moments is that we know that if there's a force which is a resultant acting at the location where it's supposed to be acting, then this must be the true moment that is applied on the structure, the moment that's applied on the structure. We always know this because we can calculate it from this. We can calculate the sum of the moments from all the components, and therefore we can calculate exactly what this is. So that's what we'd like to do. So we could rearrange this expression here, which is this. And so this says that if we know what the force is that's acting, and we can calculate what the moments are that are acting, then we can figure out exactly where it acts, which is what we want to know. So what we can do is we can calculate the moments just by taking the fluid pressure, right? The pressure times an area is equal to a force. Multiply that by a lever arm, y, which is this distance here, and you come up with a moment. If we go through some manipulation, we know that we're going to end up with, since the force is equal to a pressure times a depth, this here is a pressure, right? Because it varies linearly with depth, we have y squared. If we substitute this value for the moment into this expression, so this is the value for the moment we've just calculated here. This is the value for the force, which goes on the bottom. So these are these two values here. Then we end up with a term which includes y squared divided by y. And this is physically the definition of a moment of area about an axis, a moment which is used in mechanics all the time. And so we can split this up as a slightly simpler term, that instead of being able to define this about maybe an axis that we've chosen, we can choose it around a different axis that is one that intersects the surface. And so what we can do is we can use this as a standard result. So this is the standard result that we'd like to use. And it says that the place where the force acts, which is the center of pressure, which is not the same as the centroid of the plate, is not this cross, this X, marks the spot, can always be found if we know this standard result the area of the plate, the depth of the centroid of the plate, which is this location, but its location on a, not on the vertical, not h sub c, but y sub c from the surface, and also this here. Okay. And so these standard results, you'll have seen them in your mechanics class. I won't try and give you whiplash, but I'll show you them here. They look like this. They're moments of area. I call them moments of inertia because they're used in mechanics, but we can think of them as moments of area. So these standard terms are this, which are just products of the size of the plane. So this is a plate that we've been talking about. This is the centroid in the middle. This is the width, B. This is the height, A, which is split between the centroid half and half. And the magnitudes of these lever arms, if you like, are just products of the lengths of this figure. And what they're representing is the fact that as you go down in the fluid, progressively further down, there's an increasing pressure, but there's also an increasing lever arm on which it acts. And so what it does is it finds you the location of where things will act as you go down through it. So let's go through an example, just so it kind of cements it in your mind. The example we'll do is for a circular gate. And so the idea is if you have a gate which has a pivot through the center of it. This isn't circular, I realize that, but say the gate has a pivot. We know that if the fluid pressure distribution on this gate acts like this, if it was a uniform pressure distribution, then certainly it would act at the center of this height and at the pivot. If the pressure distribution increases, you would go further down, then you could surmise that the weight of this extra pressure and its moment at the bottom, we've already said, would be 2/3 of the way down. What is the location of that for this particular plate, this circular plate? And so what we're going to do is going to need the area of the plate, which is pi r squared. We're going to need the second moments of area of the plate, which is around the y-axis, which is really the only one we're interested in, which is pi r to the 4 over 4. And it becomes a recipe. Okay, so let's go back up to this. So this is the question. This is a plate. Happens to be like a flutter valve in a carburetor. It just pivots on its center line. So imagine, doesn't really matter right now, imagine that it's pivoted around this center of the plate. And the question is, what's the magnitude of the fluid pressure which acts on one side of this plate, and where does it act? We know that if we kind of drew this plate like this, that the pressure distribution as we go down would be something like this. And so the pressure distribution would be this. If we wanted to, we could divide it up into two parts and think about a uniform pressure distribution, which we know where the force from that would act at half height. And this other distribution here, we know the force from the triangle, let's do this force from the prism, would act at 2/3 of the height. And so from these two, you'd expect that if you took a moments around this, you'd expect that the resultant would be somewhere below the centroid of this plate, just from looking at this physical distribution. So if we wanted to calculate the force, what's the force going to be? Force is going to be equal to the unit weight, the depth of the centroid times the area. Depth of the centroid of the plate is what? Thank you. Area of the plate, pi r squared. You have everything you need to know if you know unit weight is 9.8 kilonewtons per meters cubed for the water to be able to figure out what Fr is. So that's not so difficult. But where does it act? It acts at some location yr. And this distance here to this point here, which we don't know, is y sub r. We think it's going to be below, it is always going to be below the centroid, or at the centroid. You can rationalize that. And the way we calculate it is just by using this formula. The reason it has to be at the centroid of below is because it's given by the depth of the centroid plus some number, and this number is always positive. The depth of the centroid, remember, this plate happens to be vertical. So h sub c from this plate is 10 meters from the surface vertically downwards. Also, y sub c is 10 meters vertically downwards. If the plate was inclined, then h sub c would be 10 meters down to here, but y sub c would be more than 10 meters because it's waiting to intercept the surface away from us. And so you have to allow for that. Not the case here. So what are the numbers we need? We need I think it's the first moment of area around the centroid, which is Ix sub c, which is, if we go down, it was something to the power 4, right? It's this number here. Pi r to the 4 over 4, standard result. So this is this. This is the first moment of area around the centroid, as it's called. The depth of the centroid, we know. The area of the disk, we know. And we end up, if you throw numbers into here, we end up with YR being 10 meters deep, which is the depth of the centroid, plus this number from this fraction, which ends up being 25 over 40, which is 0.62 meters. So the depth to get to this centroid from the surface, which happens to be a vertical depth, is 10 meters to the centroid, plus 0.62 meters in addition to it. And the reason for that is because of this distribution here. If it was a weightless fluid where the fluid pressure was just uniform, the pressure acting the centroid would act at the centroid because of this prismatic distribution here. But because of this triangular distribution, it's not. And so this is the amount that's below. So it always has to be below the centroid by some amount. And the amount by which it's below is given just by this expression here. Again, reiterate, y sub c is the slope distance from the surface. I'm not sure if it's probably a better picture. Yeah, okay. So this is for a plate. This is the center line of this plate, half height, half length. This is the centroid of this plate, half above, half below. The depth of the centroid is to that point. The slope distance y sub c is not. And so that's important. That's important. And by the way, the one thing we haven't said is that the fluid pressure is acting on the plate. The maximum fluid pressure is always perpendicular to the plate. And so the maximum force is always acting, resultant force is always, the maximum is always perpendicular to the plate as well. All right? So we have the depth where the fluid pressure acts. The other question we could ask ourselves is, so we know now that it acts on this line which is 0.62 meters below the center. Where along this line does it act? Does it act here? Or does it act here? Or does it act here? Or here? And so the other way to do this is to, we won't derive it, but to invoke a very similar expression to y sub r. And that is this expression here, x sub r. This is the x-coordinate where the fluid pressure acts, and it's equal to the second moment of area about xy divided by the slope distance of the centroid of the plate, the area of the plate, and the location of the centroid. The location of the centroid of the plate is exactly the same as this thing here. This is the balance point. And so the centroid of a circle, of the circular plate, has to be this location here, right in the middle. And so what each of these equations are doing, they're basically they're finding the centroid of the plate, and they're taking moments about it, both in the vertical direction for the pressure distribution which increases with depth, and it's looking at this moment around the centroid and rationalizing the point where that moment is zero. And that point where that moment is zero is 10.62 meters below the surface. And now it's going to look for the moments around the centroid in the other axis, which is the vertical, which is around the y-axis in this case. And it's going to find out just by symmetry, if you use this, if you use this expression here, this is the standard result. And if we look for what that standard result was in this, so no great surprise that because of the symmetry of this plate, if this is in a water, that the moments trying to turn it from fluid pressures acting on this side, pushing it into the page, and for fluid pressures on the left-hand side, pushing it in the page in the other way, the neutral axis has to be this place here. And so when you take this value of the first moment of area around in the x direction with respect to a pressure distribution that varies in y, which is what this terminology means, and around the centroid, when we add that term in, then no surprise that you look here, this term is zero, and so this is just the location centroid. And so we know from this that this force acts at this point here, which is 10.62 meters below the surface of the water. Okay. Why would we care? Why would we ever care about that? Well, one thing could be is that this could be a gate. And so if this is a gate, and here, by the way, we've done this calculation for the magnitude of the force, which we did up at the top of the page anyway. If this is a gate and this is the axis around which it rotates, then what we could do is we could calculate what kind of forces we'd have to hold in place to be able to keep it from moving. We know that for this distribution, that the fluid pressure varies from the surface like this, and so its distribution would be this. And we can divide that up into two different components if we wanted to. And so what we know that if this is flooded on both sides, the forces acting have to be in equilibrium. Same fluid pressures acting on either side. There's no net moment on this. But if you drain the right-hand side, then all of a sudden there is a net force acting. Now all of a sudden the force acting here is zero. This is the pivot point, and this is the force that's acting due to this distribution. So in other words, the resultant acts here, which is Fr. We know its magnitude. We know where it acts. And therefore we have everything we need to be able to calculate, for instance, what is the force that this barrier should be able to hold to be able to stop it from moving just by taking it as a free body. The free body is a pivot here. It's a force here that acts at some distance here, which is 0.62. We know that this is acting, what was the radius of this plate? Was it 5 meters? No, it's less than that, right? It was 5 meters, I think, right? And so this height here is equal to 5 meters. And so what we can do is we can just take the moments. 5 meters times F shut, which is going in this direction, and 7,700 kilonewtons times whatever the lever arm, which is this, is acting in the other direction. The only thing we don't know is this, and we can solve for that. Simple as that. And so, and so that's it. That's the reason for doing it. And so it's important to know exactly what the components are that are being used here. We can always use them. I guess it was up here. It's always true that well, I guess they're on here. It's always true that these magnitudes are what they are. We just have to remember exactly what they are. So with the danger of being pedantic and repeating this, I will repeat it. So these are the three expressions that we've dealt with. The magnitude of the force is equal to the pressure acting at the centroid of the plate multiplied by its area. Always true. Doesn't matter if the plate is vertical, doesn't matter if it's horizontal, doesn't matter if it's inclined. H sub c is always the depth to that point from the surface. Depth from the surface because the pressure on the surface is zero and it's increasing linearly by the unit weight times the depth to that point. Always true. This H sub c is always the vertical dimension. This is always the unit weight of fluid because this is the fluid pressure that's acting at the surface. If we want to get the resultant, well, you know Pythagoras. If you want to calculate where it acts, it does not act at the centroid as we've just seen. The centroid of this disk was 10 meters below the water. The center of pressure was 10.62 meters below the water. It's always either at the centroid or below it. It would be at the centroid, for instance, if it was horizontal. You'd be able to figure that out. And you'd figure that out because the fluid pressure distribution across this was uniform across it. And so the lever arm for the fluids acting on this side of the centroid and this side, the other side of the centroid, would exactly balance themselves. And you can always get the location of the resultant from these two expressions. This is by far the more important expression because it gives you the depth at which it acts, which is typically what we want to know. This gives you the horizontal location which it acts, which you can almost figure out by inspection from what we've talked about before about just balancing forces. So take this gate, where if you try and rotate it around this axis, you have exactly the same force acting on the left-hand side as you do on the other side. So it typically is the centroid of the point. Not always, but typically. And so in this, the other important thing to really make a case for is that this is the slope distance, not this. So very deliberately we've used h sub c and x sub c, and that is a very, very important distinction to make. This is h sub c, the distance to the crosshairs on the plate, the balance point on the plate. If the plate is inclined, then y sub c is also the inclined distance. If it's horizontal, then y sub c, I guess, is infinite, but you don't have to worry too much about that, because if y sub c is infinite, then you know that the pressures acting on that plate always look like this, and so always, well, the depth of the centroid, the depth of the center of pressure has to be on the plate. The plate is only at a single depth, and therefore you can calculate it. So there's no ambiguity. Obviously, when y sub c is when this is horizontal, y sub c goes to infinity. But you can circumvent that by just the observation that you can rationalize that yr, the depth to the location of the point of action, has to be actually in the plate. And so you know it immediately. Okay. There is an example here. We're kind of well, yeah, let's do it. Got 2 seconds to do it. Same kind of analysis. You have a okay. Yeah, no, I won't mention it. So you have an example here. You have a gate which looks like this. You want to calculate what magnitude force you have to apply here to keep it closed. You can draw a free body of that gate, which would have a horizontal force acting horizontally, a vertical force acting vertically, and a force, uppercase P, acting horizontally, and it has a rotation around this. If you can find the lever arms of this, LH, LV, and you know this one, you can write moments. And so if you write moments in the clockwise direction, then what you have P times 4 meters has to be equal to FV times LV. This is also going in this direction, plus FH times LH. You want to know what P is, so you want to know what each of these are. The vertical force is always going to be equal to the depth of the centroid of that surface times the unit weight times its area. The length at which it acts for this, where's it going to be? What's LV going to be? Two meters long. It's horizontal. This is the balance point. Has to be there. No calculation needed. FH, you can do the same calculation. It's equal to the depth of the centroid, the unit weight of water, times the area of the plate, and you can work that out. And where does it act? That's the more difficult one. And it's not going to be 2/3 down because the pressure here already starts at some large number. Right? If you drew the pressure distribution, it starts at some number here and goes down like this. And so certainly if it was a single triangular distribution, it would be 2/3 down. Certainly if it was a single horizontal distribution, it would be halfway down. But it's somewhere between those. And so what you have to use then is the same formula we used for the gate. This one here, to be able to calculate y sub r. So you need to calculate y sub r along here. And if you know y sub r, then you know what LH is by subtraction. So it's worked there, so have a look at it. It's worked, I think, in the previous videos, so you have some other resources to look at. Yes, sir.